In this lecture, we'll extend the concepts of the dot product and the cross product to describe the plane. So this is really, we're transitioning from vector geometry to calculus, and then this will lead on to vector differentiation. As I said before, 1D to 2D, easy enough. We all know the line. 2D to 3D, it's about the plane. And you have to make that extra little leap in your thinking. So we need our cross product, which gives us two vectors and the third. Why we need that is actually to think about the plane. We want to find a vector that is perpendicular to that plane. That means that any vector on the plane, when you do the dot product of it with the thing that's perpendicular to the plane, will always be 0. There's our little matrix form. I personally think this is the best way of calculating it. It's clean, you can line it up, you can see which each part, and also you can see where something goes wrong. Once again, to emphasize, do remember the minus k, the minus on the j part, the minus in the middle part. So let's start with the line we know well. To get the line, we have something that's a slope, and we have a constant. So we also have, what do we need to define this line? To define this line, we need a point on the line and the slope, or 2 points. y2 minus y1 is x2 minus x1. Always remember that formula. So that means we have two different ways of defining it. So the first way, we give them a point, 3, 4, and we're given the slope. The reason why, you should all know this, of course, but the reason why I want to emphasize this, there are two ways of getting the formula. Yeah? So how do we get the intercept? Well, what we do is we know that the point y, we know the point x, and we know the slope. So we work our way backwards. We go 4 is equal to slope times x, and see that. And now we get our formula. So given the two values, we find out the c. Or we have the 2 points where we get the slope, that's y2 minus y1 divided by x2 minus x1. Once again, our slope is like before, 5. And c, we put the values in. And note here, I put in the different values because what's the harm? Both points are on the line, so therefore both points would give the same value for c. So another thing is, if the line y is equal to mx, then the perpendicular line is 1 over m, minus 1 over m. So that's just a little thing. This is how you do it. And if it's parallel, it's the same line, but the c is different. It's a different value. These are just little facts we know from junior cert. So how do we think about the plane? So the plane doesn't have just an x and y. It has x, y, and z. Yeah? That's so important. Now the formula is more interesting. It has an x, y, and z because there are all these points that are on the plane. And what makes the plane unique is the normal vector n. The normal vector n is what is perpendicular to the plane. So any point on the plane is perpendicular to n. So the dot product of any point on the plane is 0 with respect to n. Yeah? Because if you think about it with the x, y, and z, z pointing up here is always perpendicular to everything in the xy plane. Yeah? So this is our xy plane. That is always perpendicular. That's invisible. My finger is always perpendicular to the plane, no matter where it is. And that's the rationale for it. That's why it uses the rule from the dot product that says any vector is perpendicular, its dot product is 0. So that's what we know. So we have to work our way to find those values. So n, it's a bit like our slope, but it's a perpendicular point. Because why is it the rate of change? So our n is a, b, c. A is the slope of the x direction, b is the slope of the y direction, c is the slope of the z direction. Yeah? Or it's just always x, y, z. And then or 0 is a point on the plane. I call it the origin, but really any point on the plane, like any point in the line, can help define a line, any 2 points. And what we do is we do the dot product of a bracket or minus or naught. And that gets their formula. The reason why you do the subtraction is it centers it all around 0, 0. That's really all the subtraction is. So in Euclidean space of any number of dimensions, a plane is uniquely determined by any of the following: a point on the plane and a perpendicular vector. 3 non-collinear points. So there's 2 ways of doing it. So here is our example where we're given the normal vector and a point on the plane. We use this formula and we put the values in. So our normal vector is 1, 2, 2. Then we always have to have x, y, z. X, y, z is because the line has an x and y. The plane has x, y, and z. A hyperplane, which is 4-dimensional plane, will x, y, z, w, an extra variable. Yeah. So what you have is 1, 2, x minus 6, y minus 1, z minus 1. And then you multiply it. It's 1 times x minus 1, 2 times y minus 1, and 2 times z minus 1. That's exactly what we have here. And so what you end up with is, and it's so important, this is equal to 0, this is equal to 0. And that's by definition. So what you have here is x plus 2y plus 2z minus 10. And that can just be rearranged as 1x plus 2y plus 2z. Yeah. Note, here the x, y, and z, that's just a normal vector. So if I gave you the formula for a plane, you could find out what normal is. It's just 1, 2, 2. Yeah. How can you check if this is right? How can you check a point is on the plane? So we said the point 6, 1, 1 is on the plane, so we put that in. 1 times 6 plus 2 times 1 plus 2 times 1, and that's equal to 10, and therefore it's on the plane. Now, what if we're given 3 points, u, v, and w? Yeah. What we have to do is we have to make a vector, a new vector here of v minus u, w minus u. You always subtract the same one. What that does is it resets the vectors to 0, 0, 0. Yeah. Then you have to do the cross product of these. So that's a bit of work, but not too bad. And now that gives you a normal vector. And then everything else is the same as before. You have your normal vector. I use the point v here, but you can use v, u, w. All 3 points can be used. Don't worry which point to use. And note that's equal to 0. That's equal to 0. And that's how you can rearrange it. And it's the same as above. I decided to use points that will give you the same answer. How do you check if a point on a plane? I demonstrated this. All you have to do is put the values. So minus 18 into 3, 7 into y, 7 into z, and see that it cancels to 10. It is. But plus 18 into x, 7 into y, 7 into z, it does not cancel, so therefore it's not on the plane. That's how easy it is to find out if something's on the plane. So what happens instead, you're given a point. If you're given a plane and asked to define a point in the plane, what you just have to do is x and y can be whatever you want them to be, or y and z, and then gives you x. You choose any 2 x, y, or y, z, or x, z points to get the y. Yeah. How do you get a point on a line? You put in the x and it gives you your y. Here, because 2 dimensions, you have to put in 2 values. So you use the cross product to define the normal vector, and the dot product is what drives the formula for the plane. Hopefully each of these together will make sense. And the first tutorial sheet is just doing loads of questions, calculating these.